Yeah, so far during the workshop, I've heard a number of talks about either porting codes to work on the GPU or even just starting from scratch and building potentially CUDA-based codes to run on the GPU. This talk is going to be about a performance analysis library that I've written or actually modified to assist those developers in identifying code bottlenecks and potentially at least giving some idea about where the places are and what kind of things they might be able to do to address those bottlenecks. Brief outline. Okay, so the name of the libraries is GPTL. A number of people here in the audience have used it. It's in the CESM, and Wei mentioned it in her talk yesterday. So the idea is this was originally written to run on the CPU, and I wanted to modify it because there was quite a bit of work going on when I was working at NOAA, developing models to work on the GPU. So I'll give a brief summary of the CPU usage and then a bit about what's behind the motivation for providing this extension to run on the GPU. Bit of a design overview in terms of what the code is going to look like. GPTL mods since 2017. Actually, it turns out at this workshop 2 years ago, I gave a somewhat similar talk. It was on the same code. And at the time, it was in I guess I'd say a semi-functional state. There were some bugs that needed to be worked out both in the application code and on the system side. And then got a different job and didn't have time to work on it. But then recently, I've kind of wrapped things up and gotten to a point now where I think it's in a good functional state. A little bit about the system software requirements, kind of related to the issues that have happened since 2017, and some examples from simple analytic codes, but then also an example from a real model where we've instrumented some of the expensive code regions, a little bit about what else still needs to be done. A brief summary on the CPU functionality. Again, a number of people are familiar with this. The idea, again, in the original design of the code, this is just for the CPU. This has been around for many years now. The idea is I wanted to have a library that you could put very simple instrumentation in, start and stop, sentinels, and just use a character string to say, what's the name of this region that's being timed. And it's also, for running on the CPU, it's a thread-safe library, and that's why in this particular example I put, there's an OMP parallel loop. You can go ahead and just stick GPTL calls inside of a threaded region, and it works just fine. Let's see any of this. Blah, blah, blah. Yeah, that's everything I wanted to say there. And here's what just an example of what the results look like. You notice how there's nesting, so it shows that the outer root, like FV Dynamics calls FV Dyne loop, calls Dyne core. This particular example happened to be out of the FV3 model. And yeah, again, thinking about Wei's presentation, she had shown, it was very nice, using GPTL, on the CPU, it also has this ability to auto-instrument a code. In other words, like the Intel compiler, the GNU compiler, PGI also provides a flag that the compiler will actually auto-instrument your code from at the function level, so you don't even have to add these start and stop calls, and the compiler-generated entry points are tagged by the library for start and stop calls, and it will automatically then generate a call tree when you call the finalization routine. And this is all on the CPU level. Unfortunately, on the GPU level, they don't, for the moment anyway, the PGI compiler doesn't provide a similar kind of flag. So for the GPU instrumentation, it all has to be done by hand. Now, just a little bit to go into some detail on, what are the motivations for actually writing a separate library. I mean, NVIDIA provides things like NVProf for profiling, but one of the real motivations for me was sometimes you want to know at a finer granularity, where the time is being taken inside your kernel. And so in the design of the library, I wanted to be able to allow the user to put start and stop calls actually, wherever they wanted, wherever they suspected there might be a performance problem inside of their code, and just put these start and stop calls just like on the CPU. Also, one of the motivations, load balances or load imbalance can often be a performance problem. And so what I did in the design is I wanted to make sure that there was statistics printed out when when you call a print routine that actually analyzes timing used, for the particular regions that you've instrumented on a per warp basis. What's the most expensive warp? What's the least expensive warp? Again, very similar to the idea on the CPU where it's thread safe. You can just put these calls, inside, so that the library is called on a per warp basis. Obviously, you want to minimize the timer overhead, and that's going to be an issue that I'll talk about a little bit later. I've done sort of most of the upfront things that were causing some of the timing problems that from 2 years ago were pretty serious. One was related to string manipulations. The last thing you want to do on a GPU is be calling things like string compare. Is much more overhead than doing that on a CPU. I tried to retain as much of that simple API approach as possible. Just call start and stop and then give it some sentinel that tells you, what region it is that you're timing. It's a little bit more difficult to separate, that ability from just passing in a character string because, again, as I said, you don't want to be doing a lot of character data manipulation inside of a computationally intensive kernel running on the GPU. This last one was the constraint was driven mainly by the fact that the work that we were doing on the models was in OpenACC. So the idea was to build this library to assist the model developers in finding out where the code problems were. And so that's all I'll say there. Okay, so one of the keys, what do I need to be able to gather timing information is just critical. There needs to be a system-provided routine and to count either wall clock time or clock cycles. And it turns out there is one. In CUDA, you can call this routine clock 64. It's a 64-bit cycle counter. It doesn't count seconds like get time of day does, but that's not a big deal. You can just count cycles. And so that was the real key that once I found out, that exists, I was convinced it was at least possible to build this library extension for use on a GPU. And then in that development, I chose to just write all the code for the extension. It's all written in CUDA so that, as it turns out, you can, if you've got a pure CUDA code, the timing library will work just fine. And likewise, if it's OpenACC with just some real simple high-level wrappers, very thin wrappers, you can profile your OpenACC code and, in fact, mix CPU calls with GPU calls, and I've got a couple of examples of that later on. Let's see. Yeah, and I mentioned store the timers, once per warp. There's no point in doing this once per thread because, a warp is essentially like a vector on a CPU that all of the little individual itty-bitty CPUs in a warp are going to finish the warp calculation at the same time, so there's no point in timing each individual thread. And so that saves, a factor of 32, given the warp size is 32. Let's see, also then in the output, what I do is to linearize the warp number. You've got 3 different thread indices and 3 different block indices, and mainly for efficiency, I linearize that warp number, both internally the calculations and what gets printed out as part of the output when you call the print routine. Okay, so the design overview. Number 1, sort of up front, and this is another change from the status in 2017. One of the mistakes that I made originally was whenever you'd get a new timer, I would call malloc down on the GPU, which it turns out is a terrible thing to do. And so the way to resolve that was just allocate the space for all the timers that you're going to use up front from the CPU with a CUDA malloc call for just, you need to tell it, here's how many timers I'm going to need, and here's how many warps I'm going to use. And then to address the character timer name issue, again, the character handling, you don't want that to be down on the GPU. So the way I handled that was I create an integer handle, which is then used, that's what you pass in when you call the start and stop routines when you're on the GPU, so that there's no character manipulation going on inside the GPU. Yeah, I mentioned the linearized warp number, and given warp start, stop, and accumulate. Yeah, so the idea then is it's similar to the CPU code, the computations internally, the start and stop. You call those start and stop routines, and then the library itself will fill in, as the start-stop pairs get added up, it'll present timing statistics on a per warp basis. And the printout all happens on the CPU. I think I mentioned all of this, the no more malloc and no string function, so I'll skip that. Okay, at this point, again, I'm not positive what the exact cause was for some of the issues I had in the past. It would work on some applications and not others. And it seems like once I went to PGI Rev at least 18.3 and the CUDA Rev at least 10.0, all the problems went away. So I'm going to say as long as you have those Rev levels of CUDA and PGI, the timing library should work just fine. There are some issues with, what do they call it? Compute capability. I'm using CC 6.0, and if you don't have the right version of CUDA and PGI, it may complain. But I've actually been using 19.4 and CUDA 10, and I've not run into any of those issues. Just very briefly, yeah, I won't say much about this because most of these issues have gone away. It was a big issue in the past that MVCC doesn't provide on the GPU any of the string functions. You got to roll your own, and I still have to have some string functions in there because of the startup that happens. There's no realloc, no varargs. Realloc is no longer an issue at all because the allocation is all done up front. No sleep routines, and some of the issues about Printf. Here's a code example with a simple code where the colors here, the green indicates CPU code, and the red is the GPU code. And the idea here, the main point I want to get across, is that you can actually mix. If you've got your OpenACC code, you can go ahead and still call the CPU-based GPTL calls, as well as the GPU code, GPU calls, and then the library, when it prints out the results, will sort them out between the CPU and the GPU. And here's an example of what comes back. You get the total number of calls, the number of warps that were involved, and again, this is that linearized warp number. And what I call holes is just where there was a region that never got a timer called for it in this particular simple example, which was actually from that earlier code sample. there weren't any holes at all, but you get a max and a min across the warps. Let's see, in this particular example I put together had a variability of timing from, a low amount of work for the least amount of work for thread 0, and then the most amount of work for the highest warp number, which, 0 through 111. So you can see that the most work that comes back, took like 1/10 of a second for this square root little test routine, was on the highest warp number, and the least amount of work was for the lowest warp number. And then again, this is that same sample code where the load balance is even, you get, sort of a random warp who's responsible for the max, and the min is essentially the same amount of time. I just wanted to illustrate how this can be used to find out, whether there's load imbalance in your application or not. And then this example is from a real OpenACC code. In this case, I'm using the NIM model that was developed at NOAA a number of years ago. A couple of the developers are right here in front of me, Marc Govette and Jacques Milkoff. Again, it's kind of the same idea that you want to call the initialize the handle routines outside of the computational part, but then once you've got these handles, that's what you pass into the start and stop routines. And I've culled down a whole, these little places where the ... is, there's a whole bunch of computations being done there, and I just wanted to illustrate how we put these timers around various parts of it. And then the result that comes back, in this particular example, I turned these guys off. These were, you can put the start and stop calls right inside of the tightest loop if you want, but you're going to run into some overhead problems. And I'm going to say there is a bit of an overhead problem as is. I'm going to continue to work on improving the efficiency of the library, but you'll notice, so this VDMINS3 I put in red because it's the most computationally intensive part of the NIM dynamical core, and you notice, okay, to call all these timers, you call them a whole bunch of times, and it took 26 seconds, or almost 26 seconds. And then the next test I did was I just turned off all these other timers. I just commented them out, and so the comes back with 0, and it's like, well, okay, that took 17.3 seconds, so it sped up a lot by turning off the timers, and that shows there is a fair, that was like a 50% overhead in actually calling the timers. I think it still can be useful, particularly where, you're inside of a given routine and you do want to find out how much does this part cost versus this other part cost, and then, compare those numbers, and that can still be useful. You want the overhead to be as little as possible. I don't want to give the implication that, hey, this is a really serious problem. It's just something to be aware of, that if you put your timers at too fine-grained of a level, you are going to see it in terms of the the overall runtime for the routine or the application being profiled. Yeah, and that kind of shows up here. I added this to the library. It tries to come up with an estimate of what the overhead is going to be. I'm not going to claim that it's perfect, but in this particular example, I'm comparing. The CPU overhead is around 6 times 10 to the minus 8. Whereas on the GPU, for a single start-stop pair, it's almost 2 orders of magnitude more expensive. So it's just, that's kind of is what it is. Okay, so just the last couple of slides. Where are we going next with this? It's interesting now, working with Ed Hartnett, who works at NOAA now. He has assisted, he basically did most of the work. The GPL library is now built under autoconf, so you /configure, the typical kind of thing, to build the library. And I haven't built that into the GPU code yet. I also haven't put in the ability to do summary across MPI tests. Everything we looked at there that was run on the GPU was I was just running codes on one GPU. Potentially block and thread information. It would be easy to save, you know, which block, which thread, X, Y, and Z were responsible for max and min. If people are interested in that, that would be an easy addition. Performance optimizations, I put a question mark because at this point, I'm not sure, you know, whether there's any low-hanging fruit in terms of the library overhead itself. Let's see. Oh, adding call tree structure. That would be easy to do, but again, it would make it more overhead, not less. So we'll see whether that happens or not. And again, I mentioned earlier the auto-profiling possibility, but that's going to require vendor support for, you know, providing a compiler flag to enable the auto-profiling. So last slide, this is, it's open source software. Feel free to download it and contact me, you know, through the web page there, or the GitHub spot with questions if you want to give it a try. And the branch you want, so the base code, the trunk, if you check this out, is going to be the CPU code. If you want the GPU capable part, you'll check out the CUDA ACC branch. And I'd be happy to hear feedback about, you know, features that are needed and are the features that are there useful. So that's all I had. Thank you.
Thank the speaker. And do we have any questions? So, Mark?